Okay, so let's do a couple of example problems. The first one draw a little line here. So the first one says a light rail commuter train accelerates at 1.35 meters per second. Starting from rest, so we know that A is 1.35 meters per second, and we know that V0 is 0. How long does it take to reach a speed of 80 kilometers per hour? So VF is 80 kilometers per hour. Now for me to work this, I'm going to change this number to meters per second, because our acceleration over here is in meters per second squared actually. Okay, so how do we do that? Well, first we multiply. There are 1,000 meters, 1,000 meters in 1 kilometer, and there are 3,600, 60 times 60, seconds in 1 hour. And the hours cancel each other out, and the kilometers cancel each other out, and you do the math here, and you're going to get what it is in meters per second. And it's 22 point, let's see how many we got, 22.2 meters per second. Okay, so now it wants to know how long does it take to reach a speed of 80. Well, we know that VF is equal to V0 plus AT, right? Now we know this is 0, so we can just stop thinking about that. So we have VF is equal to AT, and we know A, so we have VF divided by A is equal to T, and T is what we want. So that's 22.2 divided by 1.35. Or 16.5 seconds to 3 significant figures. Now, once we get to 80, it says if the deceleration rate is 1.65, how long does it take to stop? Okay. Again, we can use the same equation. Now in this case, VF is 0. So 0 is equal to V0 plus AT. And so we move this over, so minus V0 is equal to AT. So that is minus 80, because that's where it's 0.0, is equal to A, which is minus 1.65 divided times T. And so we take 80 divided by 1.65, and that gives us the answer T is equal to 48.5 seconds. Okay? Nope, I messed up. This, I put it in kilometers per hour and it should have been 22.2. So this is incorrect. Let's try that again. Got to make sure your units are right. Okay, so it's 13.5 seconds. Now, how did I know I messed up? I knew I messed up because this number was so much different than this number, and yet the acceleration and deceleration were very close together, so I knew I should get a number that's fairly close to 16.5. And when I got 48, I knew I'd messed up, so it's because I used the kilometers per hour instead of the meters per second. Now the last question is, in an emergency, it can stop in 8.3 seconds. So again, VF is equal to V0 plus AT. So VF is 0, V0 is 22.2, and we want to know A, and we know that this is 8.30. So the question is, what's A? And this is going to move over here and become a negative number, so our number is going to be negative. And it's going to be 22.2 divided by 8.3, or minus 2.67 meters per second squared. Okay, so that's that problem right there. Now let's take a look at this second problem. Some pilots jump from planes without a parachute and survive. If a pilot is descending at 123 miles per hour and stops in 3 seconds, what is the deceleration? Okay, we need to change this 123 miles per hour to meters per second. Okay, so we have 123 miles divided by hours, and we multiply that, and we know our 1 hour is 3,600 seconds. So that's the easy part. And there are approximately 1,600 yards in a mile. And there are approximately, I think about 1.0, actually 1 yard is about 1.09 meters. That's not exactly right, but that's pretty close. So if we take that and do the calculation, we get approximately 59.6 meters per second, which is pretty close. So we're going to go from 59.6 meters per second to 0 in 3 seconds. So we're going to use this same formula up here. And we know that VF is 0, so minus V0 is equal to AT, and A is going to equal minus V0 over T, and V0 is 59.6. Put a minus sign there in 3 seconds. So A is minus 19.9 meters per second squared. Okay? And what distance is traveled in that 3 seconds? Okay. You can do this a couple ways. VF squared. Let me think about this. Which one would be the easier way to do it? we know the time. Yeah, we can do it this way. X is equal to V0t plus 1/2 AT squared, which equals 59.6 times minus 9, or excuse me, times 3 plus 1/2 times minus 19.9 times 3 squared. So 59.6 times 3 is 178.8, and this is going to end up being a minus, so let's go ahead and put that in there. 19.9 times 9, because that's 3 squared is 9, and then divide that by 2 because it's 1/2. So we're going to subtract from that 89 point, and we don't have to do significant figures until we get to the answer. So 178.8 minus 89.55. So we've traveled 89.3 meters. Again, if you have any questions about how I did these, bring them up in class on Monday, okay? Okay, so let's move on. Now, let's look at falling objects. Now, the biggest difference between what we've been talking about up to this point and when we talk about falling objects is that acceleration is fixed in a falling object. Acceleration is gravity. So when something is free falling, it's called a free falling object, and the acceleration that that object undergoes is gravity. And gravity in the metric system is 9.8 meters per second squared. So our velocity equation that we had before, the only change now is the fact that instead of an A, we use a G to represent gravity. And our distance, and notice that I've used Y here, and the reason I use Y is because we're traveling in a vertical direction instead of a horizontal direction. So our displacement is going to be wherever we are initially, plus the displacement that's due to the initial velocity and then the effect of gravity. And again, this equation, which we had before, changes in a similar fashion, again using G and Y because it's in the vertical direction instead of X's. So here's an example of what happens to if we're looking at position versus time, velocity versus time, and acceleration. First of all, if you look at the acceleration, you have a person that throws a rock up, and this is what happens. Initially it takes off, and its position goes up and up to a point. It then stops, okay, and then begins to travel back down, okay, and we all know this. We've thrown things up in the air. So this is the position at each point. And these are the velocity vectors. So this is the first one, and the second one, and the third one. And notice that there's a change in direction. The length of the vector is how the magnitude, So it's longer initially than acceleration is working against it, or gravity is working against it, so it gets shorter and shorter until it reaches the top, and then it begins to get longer and longer again. So our velocity starts out in the positive direction and gets slower and slower until it reaches a certain point, which corresponds to this peak here, and then velocity is 0. And then velocity begins to go negative, so it's in the opposite direction. This is in the upward direction, this is in the downward direction. Gravity never changes. Gravity is always the same. This is just another way of looking at it. You start at y equals 0, you throw it up at 13 meters per second, and its displacement is up to a point of 1.8 meters high, and you notice the velocity vector gets smaller from here to here. It's 13 meters per second here. It's not calculated here, but in coming back down, we have another y, which is inferior in terms of position, and the velocity vector has changed directions, and you notice that it's getting longer as you travel down, and down here it's longer, and it's a minus because it's downward deflection, and that is what happens when you throw something up in the air and gravity acts on it. Here you're just dropping it, or actually you're throwing it downward at 13, and then gravity acts on it, and when it hits this point right here, it's going the same velocity. And the reason is that when you're going up, it's up at 13. At this point, it's traveling down at 13 meters per second. And so that's why the velocity at this point is exactly the same. So here's a free-falling object. The displacement is here, and as gravity works on it, as time passes and gravity works on it, the velocity gets faster and faster and faster. So here's the position, and here's the velocity, and it's linear because the acceleration or slope is the same, but it gets faster and faster. And this curves down, which is because each point gets farther away from the previous point.